Dear students, I welcome you for the today's lecture related to the understanding of the performance of the control systems due to the forcing functions. This is related to the first order system. We will study the performance. First we will see what are the different forcing functions, then its output, what is input for that forcing function, what will be the output for that forcing function, and what is the response for the first order system due to this forcing function. Forcing functions are nothing but the input that is provided to the system. So there is the transient response and the second is the steady state response. The transient response, that means once I have applied the forcing function, once I have made a certain change into the system, I have introduced the thermometer to my body and there is a change. The thermometer temperature that will increase slightly, and while the change is observed from, if the initial temperature that is 95 degrees Fahrenheit and it is going up to the 98.6 Fahrenheit. So how that temperature is increasing, that is nothing but the transient response. The transition में का response जो कुछ रहेगा from 95 degrees Fahrenheit to 98.7 degrees Fahrenheit, ये जो टेम्परेचर का सफर है इंक्रीज होने का, वो किस तरीके से होगा, उसका बिहेवियर कैसे होगा, that is what is our transient response. And there is a steady state response. Once the steady state that is achieved, that means the thermometer bulb temperature and the body temperature, they are in equilibrium. The same temperature of the body is that of the thermometer bulb. That means the body temperature and temperature indicated by the thermometer is the same. This is called the steady state response. It will show a same body temperature, for example say 98.6 degrees Fahrenheit. That will be our standard. So that will come to that steady state and it will remain to that. There will no change after it attains the steady state or the equilibrium state. So these two types of responses are there, that is, one is transient response and second is the steady state response. Now what are its design specifications, how to get compromise for this, that is the different story. A distinct advantage of the feedback control system is that ability to adjust the transient and the steady state response. We can easily distinguish that. Now there are different input signals, different forcing functions. Different input signals, they are nothing but the different forcing functions. The standard forcing functions are step input, the unit impulse input, the ramp input, the sinusoidal input, sometimes the parabolic input also. Out of this, from the chemical engineering point of view, the step input, unit impulse input, the ramp input and the sinusoidal input, these four are more concerned. When you talk about the biotechnology, then your parabolic inputs there also becomes important. Like the bacteria, they are increasing, population increases parabolically. Now first is a step forcing function. One by one we will study what are these four forcing functions. After that we are going to apply the individual forcing function to the first order system and we'll see the response. Response means what will be its output. Output is nothing but the response. How that system is going to behave. Thermometer bulb कैसे temperature increase करेगा. That is what a response is there. I suppose in this pandemic situation, all of you have observed the thermometer temperature variation. Nowadays, there are digital thermometers that is available with us. So we can easily observe and note down the temperatures for that. Initially, the thermometer variation in that temperature is drastic, fast change हो रहा है. 95, 95.6, 95.9, 98.4, 98.6, like the temperature increases fast. However, after certain time the temperature increases slow once it is trying to reach to the steady state. Now this is the first forcing function, that is the step forcing function. Now what this step forcing function means, एक स्टेप में चेंज हो रहा है. मेरे बॉडी का टेम्परेचर एक है एंड द थर्मामीटर टेम्परेचर इज इंडिकेटेड इज डिफरेंट. से 95 degrees is the temperature indicated by the thermometer and the body temperature is 98.6 degrees Fahrenheit. So that thermometer has been incorporated to a step change. That means a step change, the value of the input is held constant. Value for the input is held constant, and at time t is equal to 0, its value changed to some other value which is maintained for all subsequent values in time. When I am putting the thermometer to my body, then the body temperature is fixed. That means I have provided a constant, it is held the constant value. So the constant value, that is nothing but the body temperature. This is what the input temperature is. Body temperature is nothing but the input temperature. And its value change to some other value. That means my body temperature change has been changed to 98.6 degrees Fahrenheit. And it is maintained throughout constant. That means initial temperature, that is 95 degrees Fahrenheit. Body temperature, that is 98.5 degrees Fahrenheit. So now if you want to put this mathematically and graphically, it's a function. Ft is a function and it is changing with the time. Initially, the temperature is constant at x, 95 degrees Fahrenheit. X is nothing but the input, initial temperature. Initial input was 95 degrees Fahrenheit and the final input, that is what a step change is provided at time t is equal to 0. Now mathematically if you represent this, the function can be expressed mathematically, that is function of ft at time t less than 0. At time t less than 0, that means before this time the function is at 0 value. This is in comparison with a change. This is written in comparison with a change, and that is why it is mentioned as 0. Then a magnitude A provided for this step change. That means from 95 to 98.6 degrees Fahrenheit, that magnitude is A. So 3.6 degrees Fahrenheit is nothing but your A. So this can be represented as A, which is equal to the 98.6 minus 95. So this is where x is the value of the input variable at t equals to 0. This is the only accounted in for the change. Even though its value is 0, here function of ft that is taken as 0 and the magnitude A step change that has been considered. So A value will be for t greater than or equal to 0. At time t equals to 0, the magnitude is suddenly changed to A. So why is the value of the input variable after the step change is made? So function ft, which is equal to the A, and in terms of the Laplace transform fs, which is equal to A upon s. So Laplace transform of the ft, which is equal to A upon s. Ft is a function which is having the value A for time t greater than or equals to 0. So my Laplace transform ft is nothing but the A. So Laplace transform of this ft, that is written as fs. So A upon s. So this is the step forcing function. Now next is the impulse forcing function. Impulse means at a suddenly it has been changed for a small interval of time. That means I have put a thermometer and again I have taken out. So what will be the changes in the value of thermometer? That is for a small fraction. Now for temperature change, it is not too much. But when in a process fluid, if it's a pressure function and if it is an exothermic reaction, then this situation becomes more and more critical also. That means control valve is manually opened by mistake, or by use of a controller it is opened, and then suddenly it is closed by understanding that no, this should not be done. So that is why it has been closed. However, if the reactions are uh, exothermic and producing very high heat, so at that time this small mistake also can put a damage into the process. So this impulse forcing function, the value of the input increases from its constant value to the another value, and it is brought back to its final value, and the time duration for this change is very small. Time duration is very small, negligible. So mathematically, graphically, it can be represented as a step change that has been provided at time t is equal to 0. But at the same time, I am returning it back again to its original position. The value of the input increases from its constant value. It is its original constant value. It has been increased to the another value y, and it is brought back to its final value or the original value, and this time duration is very small. So time t is equal to 0, the value is increased, and at the same time t equals to 0, that the value is decreased. So change in this delta t is approximately equal to the 0. However, for actual process, for electronics and electrical systems, this value that can be smaller one. But for chemical equipment, this value can have a specific value. But it is considered to be as the impulse forcing function only. If A is the magnitude of the impulse change, so I can write A, which is equal to y minus t, and the Laplace transform of this forcing function, that is Laplace of ft, which is equal to A, because the at for a very small change in time, this is the ft is A. Laplace transform of ft will be equals to A for very small time change. So this is the impulse forcing function. Now there is a ramp forcing function also. So ramp forcing function, ramp, you must have seen the ramp which is constantly increasing. So this is nothing but a ramp input forcing function. That is, the value of the input is varied linearly with time. Value of the input, that is varied linearly with time. It is continuously increasing. So at time t is equal to 0, x is having the value 0, and after the time t, as the time increases, the value also increases. So this value also increases and it reaches to the infinite value theoretically. So magnitude of A is this thing at time t equals to t. At time t equals to t, here the magnitude will be this only. So magnitude itself is a function of time in this case. So it can be written as m, which is equal to nothing but the slope, which is equal to a upon t. A upon t, which is nothing but the slope m. So where a, that is nothing but x, y minus x. In this case, this is y and this is x. If the time that t equals to some value at this point, then this will be the y1 minus x. So A is the magnitude, the input change, which is equal to the mt. M, which is equal to A upon t. So A, which is equal to mass, slope into the time. So this slope into this time, that will give me the value of A, magnitude. So Laplace transform of this impulse change, that is Laplace of ft, which is equal to m upon s square. M upon s square. Then fourth one is the sinusoidal forcing function. The value of the input that is varied sinusoidal manner with a amplitude of variation, and W is the radian frequency. The value of input is varied continuously in a sinusoidal manner with A as the amplitude of variation and W is the radian frequency. Now coming to the graphical representation. So function ft is varying with respect to time and it is varying sinusoidally. So increasing, decreasing, but its amplitude that is fixed. What is the amplitude of increase? What is the amplitude of decrease? That is fixed as the A. And the frequency is T is the time frequency. So the function that can be represented as the time t less than the 0. Before this time, it is having a constant certain fixed value. That is the initial value we are assuming. This is talked in terms of a change. When it is talked in terms of a change, that is why we are writing this value as the 0. Now, let us see that it follows the sine wave. So, this function, that is the A sine omega t. A is the amplitude and omega is the radian frequency. A is the amplitude and omega, that is the radian frequency. This is applicable for time t equals to 0 and time t greater than the 0. Time t equals to 0 and time t greater than the 0. So the Laplace transform of this function A sine omega t, if you remember, that becomes A omega upon s square plus omega square or W square. So omega, that is nothing but the radian frequency, which is equal to 2 pi f. F is the frequency, that is cycles per unit time. So omega is the radians per unit time, that is why it becomes 2 pi f. Now this is what a first order system is. A block diagram for the first order system that has been written. And the step forcing function, that is 1 upon tau s plus 1. So the step response equation. Now we will see one by one the responses of the first order system with these four forcing functions. So first response for the for the first order system is that of the step response. We have talked the step response, impulse response, ramp response, and sinusoidal response, sinusoidal forcing function. For these four forcing functions, now we will study the response. What will be its output? सारे लोगों का output अलग अलग रहेगा because the inputs are different, so output will be also different. Now the response of the first order system. But the first order system, that means your transfer function is same. Transfer function that is not going to vary. Transfer function is Gs, which is equal to Ys, that is nothing but the Laplace transform of the output deviation variable, and Xs, that is nothing but the Laplace transform of the input deviation variable. And this becomes equal to k upon 1 plus tau s. K upon 1 plus tau s. So this is my k is the steady state gain. Now the input variable is given a step change of magnitude A. So in this case, the input value of magnitude A that has been mentioned, this is the initial value at time t equals to 0. I have been provided with a step change of magnitude A. So this is nothing but the value of A. This is the value of A, the magnitude. Sometimes it is also the M. A is nothing but the M also. So I can write the A or M for the magnitude. They are same. A and M are same. So this xt, which is equal to M, xs, which is equal to M upon S. So ys, substituted this value of the xs, that is I am substituting this value of the xs here. So ys, that will be is equal to the k 1 upon 1 plus ts or tau s. This t is nothing but the time constant of the system, that is tau also. Tau, time constant of the system. So this is 1 up, k is the steady state gain. For a mixing tank, our transfer function is 1 upon 1 plus tau s, right? And for a reaction vessel, our transfer function becomes k upon 1 plus ts. So here I am writing k upon 1 plus ts, generalized. So I have to write here also the k upon 1 plus ts into the xs value, that is M upon S. So after doing the mathematical manipulations, that is by using the partial fraction method and taking the inverse Laplace transform, you will get yt, which is equal to the M into the k into bracket 1 plus e raised to minus t upon tau. So this is what the response, yt is nothing but the response. Response is this output. Yt is the response, that is nothing but the output. What will be my output now when I am going to change this step? So output that is going to vary initially. It will be, I will take the another color for this then. So initially this is the output that is also there. Initially this is the output also, but with this step change suddenly it is going to start increasing in this manner. So my output will behave like this, and it is obtained by using this mathematical equation yt, which is equal to the mk into bracket 1 minus e raised to minus t upon tau. This is important. This is the response equation of the first order system. So now we will analyze it in details. So response equation 1 upon s, how to simplify that, that is also there. In some books, instead of writing y and x, it is written as cs upon rs, where cs is the output, that is nothing but the response, rs is the input, that is nothing but the xs. So rs, which is equal to 1 upon s, that is nothing but the step response. So rs 1 upon tau s plus 1 into the rs. After simplification you will get this thing. Applying the partial fractions you will get the final equation as ct, which is equal to the 1 minus e raised to minus t upon tau, where they have taken the unit impulse. Now if the impulse is of the magnitude m, so this equation becomes multiplied by m, and if it is with a steady state gain, multiplied by with the k. So this is what the small derivation, you can go into the details of the derivation from the concerned book. So this is what the graphical representation that has been shown. Now the yt, which is equal to the response, which is nothing but ct also, which is m into bracket 1 minus e raised to minus t upon t. Now I am going to plot this yt upon km. This is m into the k. So this will get cancelled against t upon tau. T upon tau. So t upon tau, that values I am going to put as 1, 2, 3, 4, 5 and 6. And I will calculate the value of yt upon m for this. It is simple, 1 minus e raised to 1, 1 minus e raised to 2, and that will give you the value of 0.632, 0.85, 0.95, 0.98. And this has been now graphically put as these are your t upon tau values in the x direction, and this is yt upon km. So these values will be from 0 to 1, 100%. 1 is 100%. So at time t equals to 1, it attains a value of 0.632. For time t equals to 1, it attains a value of 0.632, which is here. So this is the final value at time t equals to the 1. So this t equals to 1, that means time constant and this t, they are 1. time constant equals to the 1. So this becomes your 0.632. Then for t equals to 4, t equals to t by 4, which is equal to 0.98. So this is 0.9, that has 0.95, that has been achieved for the value of 3, and 0.98. So it is around this 0.98 value. So that means it is achieved for the value of t upon t raised is equal to 4. So this value of the 4, that is t upon t, it attains the 98% value. Now this graph that can be again discussed, that is related to this point. One is the for one time response, it attains a value of 0.632. Now if the slope, that is at time t equals to 0, that is nothing but the dyt upon m upon the dt, that is the dyt upon m upon d upon t by tau at time t equals to 0, which is equal to e raised to minus t upon tau, which is equal to the 1. So the initial value, the response is at time t equals to 0, it attains a value in one time constant. This is one time constant, this is second time constant, third time constant, and fourth time constant, t upon t values. Now why it is like this? It attains a value of 1. Initially, the temperature gradient is maximum, or whatever the gradient, temperature, concentration, flow gradient, they are maximum initially. But with the passage of the time, this gradient also decreases, and as a result, it will not attain this initial values. That means initially, if I am putting a thermometer to my body, then initially 95 degrees Fahrenheit and 98.6 degrees Fahrenheit, that is the temperature gradient, means 3.6 degrees Fahrenheit का temperature gradient है initially at time t equals to 0. But will it remain same? No. Temperature gradient will also going to decrease, because that thermometer will gain the energy and will subsequently increase its temperature, like say from 95 to 96 to 97 to 98, that increases with the time. So this temperature gradient also decreases. Initially temperature gradient was maximum, that is of 3.6, but this temperature gradient decreases, and that is why this becomes a parabolic curve. This is not a straight line. If it would have been a straight temperature gradient would have been the constant of say 3.6 degrees Fahrenheit throughout, then it will attain this path. But this cannot remain the condition. Temperature gradient cannot remain the constant as at that of the 0 time. It has to decrease, and that is why it follows a parabolic path. So that is one thing. Then the steeper the initially, the temperature gradients are higher and it decreases gradually, and this is why it attains a parabolic flow. Now the response, when it is 98%, response is would be complete after the 4 time constants. We are assuming that for 98% values it is more than sufficient. The body temperature 98% आ गया है, so it is that means I have attained the fulfillment. So in 4 time constants, now there is a question that how much time should I keep the thermometer in contact with my body? That is the 4 time constants. What is the time constant of a thermometer? That you can also check. So this thermometer, generally we say that you have to keep it for the 2 minutes. That means half a minute is my time constant. So 4 time constants I am going to calculate. So these are the different characteristics of this first step change response. Then this is what a certain example that has been shown. Now the second is the ramp or linear response equation. Now again the procedure is same. First write down the transfer function gs, which is equal to ys upon xs, which is equal to k upon 1 plus tau s. A is the slope of this forcing function. In previous case, m was the slope we have taken. Here we are writing this value as y. So this is the value of y that is there. So slope A, this is my slope A, which is equal to y upon t. This is the small y. Remember that. This is the small y. And this is the capital Y. Capital Y is the Laplace transform of the deviation variable in this case. Ys is the Laplace transform of the output deviation variable. One is the input and another is the output. Input क्या है? तो input thermometer है. Thermometer का initial temperature is the input. How it is going to respond? That is the ys. So this slope that is equal to A, which is equal to y upon t. So y which is equal to at. Therefore xt which is equal to the at. So xs which is equal to a upon s square. So ys, I can substitute this xs value, that is a upon s square. So ys a upon s square upon 1 plus ks. K is the steady state gain. Here I can multiply with the k also. So after doing the partial fraction and simplification, I am not going to discuss this because of this pandemic, the time factor that is also there. And this yt, which is equal to the a into bracket t minus tau plus a tau into e raised to minus t upon tau. So a that can be taken as the common, a into the k that is there. K will be there here. Now what it will give the output? This is what my input is. Now the second step is the output. What will be the output? Input is xt, which is equal to at is my input. Now what is the output? This is the transient response, you will say it. That is a t minus tau plus a tau e raised to minus t upon tau. This is the transient response for the ramp or linear step change. So xt is my input, then yt, which is equal to a t minus tau. If I substitute the t as the infinite, so this yt that becomes equal to a into bracket t minus tau. This term of e raised to that will become equals to the 0. The remaining term will be only a into t minus tau. So that is what yt, that is a into t minus tau. So you know the output, you know the input. So I am now going to plot a graph between the input against the time and the output against the time. So input against the time is this graph. This is what the input, that is increasing linearly. And the graph, this is the yt upon a against the time. It is this yt graph that is there. So input graph and the output graph that is there. The dynamic error that is there. So it is what? a difference of the time that is observed, and this difference of the time is the input variable and the output variable. The dynamic error is the difference between the input variable xt and the response or the output variable yt at steady state. At steady state. एक बच्चे ने दौड़ना चालू किया और दूसरे बच्चे ने भी दौड़ना चालू किया. एक बच्चा आगे जाएगा, दूसरा बच्चा उसके पीछे जाएगा. If their speeds are constant, it is like that only. The time lag that will be there. So this is the dynamic error, and this is nothing but the AT. Now where A is the slope of the ramp change. This is the slope of the ramp change. Now the time lag, what will be its time lag? That this Ti initial time to attain the same value, as shown in the figure, the input requires the Ti time and the output requires the Tf time. So the input Ti and Tf is nothing but the T minus tau. So Ti minus tau, that is the input. So xt upon A, which is equal to yt upon A, which is equal to Ti minus tau. So time lag, which is equal to tau. So time lag is tau. So this is the 4 differences I am going to